Or Sonny Whitelaw. I'm manager of BRaid, but I also do double duty in other things. Okay, so if you're a kind of depressive personality, I would perhaps suggest you leave right now. I'm quite serious. This is quite frightening stuff. I'm not going to cover all of these points. I just threw them up there as a short list of the problems that braided rivers are going to experience as a result of a changing climate. So just to go back to first principles, changing climate means that we've changed the chemistry of the atmosphere and we've changed the chemistry of the ocean as well. So the bottom line is we're going to lose and have a lot of degraded habitats, and the net result will be the collapse and extinction of ecosystems and species. Let's go back to the beginning a little bit. People keep saying to me it's just a cycle. They're dead right. Climate change is a cycle. Some of you may have heard about the Milankovitch cycles. Fundamentally, Earth orbits the sun in a wobbly. And every 100,000 years, there's quite a few cycles to it, but basically we go through warm interglacials and cool glacials. And the difference between them, 180 parts per million during the cool periods, 280 parts per million during the warm periods. There is a transition, obviously, but generally speaking, for the last few million years, that's what we've been doing. So an increase of 100 parts per million corresponds to an increase of about 6 to 8 degrees temperatures between the cold and the warm, okay? And about 120 metres of sea level. That means that Christchurch would be 65 kilometres east of where it is right now if we're in a cold period. So in the warm Holocene epoch, that's the epoch we're living in now. Let's not get started on when the Anthropocene started. Let's just call this the Holocene because it's still the Holocene until the geologists decide that this is the Anthropocene. We're in a warm period. So 200 years ago, what did you expect? 280 parts per million. Great. So where are we today? Oops. Now, bearing in mind, 100 parts per million corresponds to 6 to 8 degrees of warming and a whole lot of sea level rise. I'm just going to approach this from what they call the RCP or the SSP 5 to 8.5 scenario, and that's complete gobbledygook, but basically what it means is that looking at the IPCC reports, they produce a number of scenarios and projections, and the projections are based on how quickly we can stop emitting carbon emissions and methane and nitrous oxide and sulfur hexafluoride and all the other lovely warming gases into the atmosphere. In other words, stop changing the chemistry of the atmosphere. So we're going to use that term throughout. So just this is the worst case scenario, okay? What does that look like? Well, between the two, that's where we are. That's where we're headed by 2100, and that's what we're going to be looking at. Okay? I'm not making this up. This is from the IPCC. Most of the stuff that we're doing, most of our responses to this are based on the last 80 to 100 years or so. But we're currently pretty much in the mid-Pliocene warm period. We're not quite there yet because it takes a few hundred years to catch up with putting all that stuff in the atmosphere and actually getting warm. But that's, that's before humans existed. So we actually have no baseline. We are headed into uncharted territory. And the way we're going, if we hit that 1,000 parts per million mark, we're going to head straight into the Eocene. It's one here. 50 million years ago. So this is also from the IPCC report. It's not my spelling error at the bottom because I pinched this slide from somebody else. It was actually NIWA. We would like to think that this is, you've probably seen this chart if you've been following this trend at all. We'd like to think that we could limit warming to 1.5. Well, that's off the cards. We're probably going to hit 1.5 this year because we've got a massive El Nino. Officially started last night, according to the WMO. And we'd really like to limit it to 2 degrees because once we hit 2 degrees, a whole bunch of things is going to just tip over. And we'll talk about that in a minute. So we were hoping that we could sort of be able to have all these policies, and we signed them all in Paris, and we said we're going to do great things. The promised policies are not being implemented. And we thought, gee, good grief, by 2030, we might hit 60 gigatons. And that'd be terrible. Oops, we hit that last year. You can leave any time you like. It's not going to get any better. I thought I'd put this up because this helps paint the context of what's going to happen to our rivers. Those dark yellow areas are where the Canary Plains formed during the Quaternary, so sort of like we're talking tens of thousands of years ago. The pale cream areas That's where the Waimakariri travelled. That's where it was allowed to travel before we put, sorry, engineers, before we put stop banks up and said you can only exit at that tiny little point up there. The Waimakariri travelled south and visited Te Waihora, probably for winter, last time 600 years ago. So that pale yellow stuff everywhere, the Rakaia used to go into Te Waihora, Waikirikiri. You can see how all those pale yellow areas, that's where the rivers used to wander before we trapped them. Could that happen again? I'm not going to answer that because they did this during this lovely, stable, warm, comfortable Holocene period. We've now left that. So I thought, yeah, let's have a look and see what NIWA is saying for future projections of rainfall, because this is obviously what's going to affect our rivers from a hydrological and geomorphological point of view. This is a projected annual 5-day maximum rainfall by 2090 under the RCP 8.5. Remember, that's the worst one. Not to crash off if you live in Westport, but I think we probably all figured that out by now. Let's have a look at a really nice stable area where not much is going to happen. Let's look at a place called Glengarry. Oh, okay, so I found another NIWA report. All right, for Hawke's Bay. Glengarry, worst case scenario, by 2100 or 2081, we could get a maximum 5-day rainfall amount, do the arithmetic, about 170 millimetres over 5 days. Worst case scenario, absolutely the worst case scenario, by 2080. Oops. During Cyclone Gabriel, the Glengarry site recorded 546 millimetres of rainfall, with 400 falling in 12 hours. So my point here is that the models are not fit for purpose. It's a bit like the RMA. Someone said to me, yes, but that was a cyclone. That wouldn't happen down here. Well, yes, we have these things called atmospheric rivers. And atmospheric rivers, you can't put levees up. They're up in the sky. They're going to go where they want to go. They're going to dump their rain on the mountains, or they're going to wander north or south or wherever they like to go. And atmospheric rivers contain an awful lot of water. And as the temperatures increase, the amount that they contain, the amount the atmosphere can carry, increases. And I think this is really telling. I don't know if many have come across Belinda's story, but she's doing quite a lot of work on climate adaptation. This was just in a recent National Geographic article, which I thought was really telling. The thing to realise that change is not linear. Suppose a council has to repair a stop bank or build some other flood defence. They may decide that the flooding risk is changing by 5%, and therefore they ought to be conservative and add a 10% safety margin. Good engineering. I come from a family of engineers. That's good engineering. In fact, they should be increasing the margin several hundredfold, depending on how long you want that engineering structure to last for. 5 years, 10 years, 20 years, how long you want to amortise the cost of it. All right, that's rivers. Let's just moving on from the hydrology and what could happen to rivers. And I'll let your imagination run wild what you think might happen to the Waimakariri in the coming decades. Depends on where an atmospheric river decides to go. This is again a quote from IPCC. This is about ecosystems. And I'm covering all kinds of ecosystems here because they're relative to braided rivers for multiple reasons. Changing climatic conditions, including warming, also progressively shift plants and animals to higher latitudes, higher elevations, or deeper ocean waters. Approximately half of the many thousands of species studied on land and in the ocean already show corresponding responses, leading to, here's the key point, climate-caused local population extinctions and shifts in vegetation zones. In the ocean, same thing. We've shifted their distributions poleward an average of 59 kilometres per decade. That's so far. Our braided river birds go to the coast and the ocean to feed. So this is relative to braided rivers because the birds we're trying to protect need to go to the ocean, well, have been going to the ocean at different points. Not all of them, but estuaries are also part of the oceanic ecosystems. So together, all of these processes have caused a complete reorganisation of biodiversity over the past 50 years, especially at the ocean surface. Those species that cannot adjust or move fast enough are at a high risk of becoming extinct. On with the next, not really particularly good news. Part of the reason I put that up to is to think about biohazards, toxins, invasive species, weeds, rats, These things do really well as things get warming. Brian's talked about estuaries, so let's talk about sea level rise. For some braided rivers, this isn't actually a terrible news. We don't know how much sea levels are going to rise. This is where I did my first thesis work, so I can say it now. We don't really know how much they're going to rise. At the moment, 30 centimetres locked in. If we cut all emissions tomorrow and magically pull the excess out of the atmosphere, we're still going to get 30 centimetres of sea level rise. If things go to the RCP 8.5 level, we could get 2 metres. Going back 20,000 years, there are periods when sea levels have risen up to 4 metres per century. That's well documented. So it could get bad, but if you think about it from a braided river perspective. Now, I pinched this slide from Murray Hicks' presentation, which he gave 4 or 5 years ago at a braided river seminar. This is the Ashburton Hakatere, the estuary and Hapua there, which I'll be going down to next week. And the Hapua, the concern here is what is going to happen to Hapua as sea levels rise. Actually, it's not too bad. The whole thing is just going to reconfigure inland. Sorry about the houses up there, they're just going to go. But there's enough sediment, there's enough gravel in the cliffs of this area in order for it to feed back into the estuarine Hapua restructuring system. So we're still going to have Hapua. They're just going to go inland. We're just going to migrate inland. So that's a good thing. Actually, Rakahuri. All right, the one on the left, that's about, if you get a metre of sea level rise and you have a 1 in 100 year flood, which we're getting every second week now, either the Waimakariri or the Ashley Rakahuri floods, that's the sort of flooding you can look like. So again, the estuary is just going to migrate inland. We have a 1.88 metre sea level rise and we have a flooding from either one of those two rivers. The whole system's going to move inland. And access, well, we won't have any road access, so maybe that'll stop some of the dog walkers to go down there because, you know, the roads will be flooded. By the way, nobody actually ever modelled with both rivers flood at once. The reason being is that historically, the Ashley and the Waimakariri have never flooded simultaneously. That's what we know based on the last couple of hundred years. We don't know what's going to happen going forward. But generally speaking, from a coastal estuarine Hapua systems, it's actually pretty good news for braided rivers. What's happening in the ocean? Okay, 2010 to 2019. I took this, got this 2 weeks ago. Actually, when I got this off a guy called Zach Labe, he does all the modelling for NOAA and NASA, and he said, hang on a minute, I'm going to have to put another line at the top because it's gone off the charts. So that was when I got this from him, Wednesday, 21st of June this year. That's the average world oceanic temperatures. We are going into an El Nino. As I said, it was official last night. So things are getting hotter. When you've got hotter, you've got less oxygen. And of course, you've got migrating species, including the ones that we don't want on land and in the ocean. I put this one in because this is ocean acidification. How many here have heard of ocean acidification? Most of you. Do you know it also affects lakes, freshwater lakes? Actually worse than the ocean, as it turns out. Only a limited amount of research on it. But ocean acidification is referred to as climate change's evil twin. So it's the bad thing. The warming's okay, but the acidification's really bad. The current pace of acidification is faster than at any time in the last 300 million years. Faster than Permian-Triassic extinction. Increasing ocean warming and acidification are enhancing bioaccumulation of toxins and contaminants into marine food webs. There is currently no practical way to reverse acidification. Once average global temperatures pass 2 degrees, it will persist for tens of thousands of years. Aren't I a fun speaker? What does it do? Well, it doesn't turn the ocean into battery acid. It doesn't even turn it particularly acidic. It just makes it less alkaline. But the problem is when you have the ocean, which has been the climate superhero, because it's absorbed far greater quantities of carbon dioxide than the atmosphere, about 30 degrees worth of temperature and carbon dioxide would be that much higher in temperature if the ocean wasn't here. It's also changing the chemistry. All that carbon dioxide mixing with salt water is making it very difficult for shells to form. So we quite often get adult species and might be a little bit of pitting here and there, but that's fine. It's the little babies that are the problem. the little tiny coccolithophores and the sea butterflies that are literally the base of the entire oceanic food chain. They're not forming properly, and the little fish that eat them, there's not as many. Which means there's not about these big fish, and it means that penguins and seals and things are starving. So all of our braided river birds that go to the coast to feed, there's going to be less kai. So basically, the outcome is that we're actually in a pretty good way. Braided river birds live in an incredibly diverse range of habitats, demonstrating an ability to cope with extreme weather and changing food sources. We know that they're really good at doing that. So from the Alps to the sea, from desert-like conditions to suddenly gushes of freezing water coming down. It interrupts their nesting, but generally speaking, we know they're highly capable of these sorts of processes. So this is what we need to do. We need to do a lot more, but generally speaking, if we can keep ahead of the weeds, we can keep ahead of the invasive animals and the invasive bugs and the invasive diseases, and we can choose to give rivers room to move in coordination with large-scale restoration. If we don't choose to give the rivers room to move, the rivers will decide for themselves, we'll have no control over it. And we need to manage landscapes at scales to facilitate habitat migration, like the migration of entire ecosystems, and the hydrological function of those rivers. And this just happens to be my personal little crusade, the last one. Please stop calling our rivers and waterways and wetlands and streams drains. Because when the moment we stop thinking about them as places where we can dump our rubbish and flush our toilets, we might start treating them with respect. Thank you.